So before I launch into the force concept model with any real vigor, I do want to point something out that is just some practicalities that I think you need to have. Newton's second law tells us something that I think I need to go into. I used to not go into this, and then I found that there were problems. This side is force, some combination of forces, but we know that the left side is going to be forces. So this side is what happens. It's has something to do with the object's inertia. That's m. So inertia here, and acceleration here. Now, these are subtle details, but I'm afraid if I don't point them out, you'll miss something. You may have lots of forces acting. Lots. It could be 5, 6 forces. But what this tells you is that the direction of the acceleration is in the direction of the combination of forces. Meaning you may not actually even have a force that's pointed in the direction the object's accelerating, but the combination of forces will have a direction. So imagine if you have water and you have a boat here in the middle and a guy on either side on the banks, and they have ropes attached to the boat and they are pulling. You understand the boat's probably going to go this way. The acceleration might be that direction, even though there's not an actual force in that direction. The sum of the forces, this thing, has a direction. It doesn't necessarily have to be the direction of an individual force. It can be the direction of the combination of forces. So when we say that there's a direction, and that's what that little symbol on top means, we're saying the direction of the combination of forces is in the direction of the acceleration. We're saying that. It's subtle, but it's one of those subtleties that I need you to have bared out, because one of our problems later has to do with applying a coordinate system. And understanding the way your system behaves is kind of crucial to applying your coordinate system. The next thing is about units, and I just want to be real careful about explicitly stating this. Inertia is still mass. It's measured in kilograms. And acceleration is in meters per second squared. This is the unit of force. It is a complex unit in that it has lots of things in it, but this is the unit of force. And we have a name for the unit of force. It is called the Newton. So when we use the unit, we'll just put a capital N for the unit of force. But you need to be able to break down the unit into its more complex form and recognize it. So I guarantee you there will be multiple choice questions that say which one of these is a Newton, and it's just going to have a whole bunch of kilogram meter per second, kilogram meter squared per second, kilogram meter per second squared, kilogram meter per second cubed, and you'll have to pick it out from a list. You can always go back to Newton's second law to figure out where the unit came from. All right? And the last thing I want to bring up, because I didn't talk about it very much on Friday, mass is a complex idea. It doesn't seem like it should be very much. It's just how big something is. I think that's probably the easiest way that you guys think about it. But mass is a complex idea, and there's more to it than just how big something is. Mass does two things in nature. It creates gravity, or you can say is affected by gravity. But it also resists changes in motion. This is the definition of inertia. Resisting changes in motion is the definition of inertia. So when we talk about what mass is, it's hard to define it. I don't have good definitions of what mass is. We talk about what mass does. So when you're measuring your mass, usually you're not measuring your mass, you're measuring your weight, and you're interpreting your mass from that. But kilograms and newtons are different things. So the comparable unit for weight in English Standard is the pound. So pound and newtons are actually units for the same thing. Although oftentimes you tend to think that pounds and kilograms are units for the same things, but they're not. Pound is a unit of force, just like Newton is a unit of force. So when we talk about units, understand the difference. When you're measuring newtons or pounds, you're measuring how gravity affects an object. An object will have 0 newtons of weight in space because there's no force of gravity, but will have the same mass in space that it has on the Earth. An object will weigh 2 different things between the Earth and the Moon. That doesn't mean that that object has any more or less mass. It's just that the force of gravity is different on the Moon than it is on the Earth. Those are little details, but you need to understand all of them. It's subtleties. All right. We're going to pick a couple of simple ideas to start with. And the simplest one is probably the most ridiculous example, but it will allow us to use a whole lot of our set of steps. So I'm going to just set up a quick example. All right. There's a box sitting on a table in front of me. Do you guys see it? Okay, simple enough. So this is the force concept model. I'm going to talk about all the series of steps I want you to ask yourself, even the ones that don't apply here, okay? But we're going to get all the set of steps that we'll ask ourselves when we're going to try and do one of these problems. And it's always going to start with the same thing. I want you to start by asking if it's a first or second law problem. This is the first step in any of your force concept model questions. Is it a first or second law problem? So you have to make that decision before you go any further. And there are parameters here, but they're not that hard. But your biggest mistakes on all of your tests is not understanding a procedure. You'll have to memorize this procedure. So I'm actually going to do it in steps, just like this in front of you. And then every single time we do this, I'm going to have it up on the other screen, just the set of steps, just a set of questions you ask yourselves and how to apply these rules. So when you're asking yourself if it's a first or a second law problem, you're making a decision about how you're going to proceed. So here's the parameters. So is it accelerating? You're asking yourself this question. If it's not accelerating, it's a first law problem. If it is accelerating, it's a second law problem. Notice I didn't say moving, because it can be moving and not accelerating. It's about whether its velocity is changing or not. So when we say accelerating, please keep that in the back of your mind. Objects can be moving and still not be experiencing an unbalanced force. It's only if their motion is changing. So they have to be speeding up, slowing down, or changing direction. That means accelerating. Speeding up, slowing down, or changing direction. Now, here's the thing though. If you don't know, then you have to assume it's a second law. So like if you can't figure it out, or there's not enough context clues, or the problem is asking you if the object's accelerating. These are all reasonable questions, but if you don't know, then you have to assume it's a second law and then prove whether it's a first law. But I think we can answer this question for the box. Is the box accelerating or not? No. So this is going to be a first law problem. So that makes a decision about how we proceed from this point forward. Second step. You're going to draw a free body diagram. This is one of the hardest things that students have to do when it comes to dealing with a force concept model. Even though they don't really get to make any choices here. It's really straightforward what to do, but it's how detailed your set of instructions are. A free body diagram is a diagram that's designed to help you reduce the problem down to simpler things and observable things. It's going to try and take away distractions. So our goal is to take our problem and reduce it to something that has only arrows, and those arrows represent the forces. So in drawing a free body diagram, we're going to go in order of the forces that we have in nature. And we're going to apply rules. There are different rules for each one of those forces. So although I will not write out every single rule here, I will go over each of the rules. So in drawing a free body diagram, which is a whole thing all on its own, the first thing you do is reduce each object to a dot. I don't want to say a single dot. Each object gets its own dot. So our box becomes a dot. The idea is to get rid of the table if we're not interested in the table, get rid of the floor if we're not interested in the floor, reduce the object that we need to observe to a single dot. That dot represents the mass of the object. We're trying to get away from the extension of the object or the shape of the object. We'll deal with shape of objects second semester when we talk about how they spin. But for what we're doing now, which is called translational motion, we don't care what the shape of the object is. So we get rid of the distraction and reduce the object to a dot. We're going to draw arrows. Each arrow represents a force. I would encourage you to use a ruler for this because part of what we're going to have to do is have a certain amount of precision of measurement. So when you're drawing the arrows on your test, and we're just going to be applying a set of rules, and we're going to be looking at the forces here. So after we've reduced our objects to a dot, you're going to go through your list of forces. You're just going to go through your list of forces. Some of these are super easy. Like, is the object experiencing weight? I mean, the answer to that question is almost always going to be yes. So because of that, that's probably the easiest one to draw every time. Weight is always going to be the force of gravity acting towards the center of the earth from any object. So I think it's pretty clear our object's going to be experiencing the force of gravity. So we draw a single arrow downwards representing the force of gravity. Now, as you draw them, it is traditional for you to label them as you go. You have choices on how you label them. I like a capital W for weight. Most books will use capital F for every force and then use a subscript. These are acceptable. There are things that are not acceptable. You can't use capital G for weight, and you can't use lowercase g for weight. Those are unacceptable symbols because they mean something else. And if you try to use those symbols, you'll lose credit for that force. So these are a no-go. These are okay. Some people will actually even do this. This is less common, F with a capital G for the force of gravity. But these are all acceptable, but you can't use a capital G or a lowercase g. Now, we're always going to start with the conservative forces, but there's only going to be the one for this class. So the next thing we do is we go to the contact forces. The basic two contact forces are the normal force and the tension force. And for either of them to be active, there's something specific you're looking for. For there to be a normal force, there has to be a surface in contact with your object. So is there a surface in contact with the box, the table? Now, this part, be very careful because I see students make this mistake all the time. Normal forces are perpendicular to the surface. Normal forces are always perpendicular to the surface. One or two of you in our next test or quiz are not going to do that. You're going to draw some other way that's convenient for you. And I will take a picture of it and I'll put it on the board without your name to remind us that no, it's always got to be perpendicular to the surface in contact. It's in the name, normal force. Now, there is a surface in contact with the box, and I would say that the surface is the table and the table is horizontal. Would you guys agree? So I'm going to draw a force upwards. Now, here's where your judgment begins to come into the problem. How big should you draw this force? You have a choice, but is there anything else that appears to be acting upwards on the book? Do you see anything else pushing upwards on it, a string pulling upwards on it, or anything like that? We already know from the very beginning that we said that the net force is likely going to be 0. So if you're keeping in mind the fact that this is a first law problem, there's going to be balance to the forces acting on your object. So I wouldn't draw this just some arbitrary size. If it's the only thing pulling upwards on your object or pushing upwards on your object, and you know that that's going to be balanced, it's probably in your best interest to try and draw this arrow so that it counters the downward arrow you've drawn for weight. You are trying to draw something relatively to scale. Acceptable symbols here: normal, capital F with a uppercase N subscript. I am going to use just the capital letters like that. I'm going to use that for the whole year. I'm not going to change. The next force is tension forces. They're pulling forces, and there has to be something that is providing the tension force. We're talking about a cable, a string, your arm, a handle, something. There has to be something that's causing there to be a tension force. If there's no strings or cables connected to your object, there's no tension forces acting on your object. So are there any tension forces acting on the box? No, I don't think so. Our next category of forces are resistive forces. And for just today, the only one we're going to talk about is friction. I don't think I really defined this last week, so I think it's probably a good idea that I define it this week. Friction is a force that attempts to prevent one surface from sliding past another. I'm going to say that again because friction can become confusing, but I don't want it to start that way. Friction is a force that attempts to prevent one surface from sliding past another. So if you have a situation in which the box is going to slide, friction is going to oppose that motion. That's something else you have to understand about friction. Friction is always opposite motion. There are two kinds of friction: static and kinetic. Static also means starting, and kinetic means sliding. If the object's not moving, there's no kinetic friction, right? That's only there if it's sliding. There can be starting friction for an object that's not moving. That means there's something trying to prevent the box from sliding. Now, in our case of the box and the table, is there any need for there to be friction acting on the box to hold it in place? Can you find anything reasonable that's trying to make the box move that friction has to act to keep it in place? I don't see anything else acting on the box. So I don't believe there's any resistive forces acting on the box. I'm going to leave them out. Now, there are other resistive forces. We'll introduce them as we use them, but the most common one that we'll have is air resistance. But we're going to not deal with air resistance for a couple of weeks because air resistance is complicated. All right? Now, you're not done when you've gone through your list of forces. There's more that you have to do, but as you'll notice, I'm kind of running out of space here. So are we all good with that so far? All right. So the next thing to do, and this part is every bit as important as everything else we've done, even if it's a little ridiculous for this. After you've gone through your list of forces, the next thing you have to do is apply a coordinate system that you can use to break your forces up into components. This one really doesn't need very much, but a coordinate system is exactly what it sounds like. You are going to apply over the top of your drawing an X and Y. This is not arbitrary. There are two rules to follow. If the object is accelerating, one dimension has to be in the direction of the acceleration. If it's accelerating, you have to put one of the directions in the direction of the acceleration. If not, you have infinitely made your difficulty level so much higher. So if you can, put a direction in the direction of the acceleration. If it's not accelerating, you want to match as many forces as possible. The more forces that are not on your coordinate system, the more trig you have to do. So if you want to reduce how much trig you have to do, try and line up your coordinate system with as many forces as possible. Now this one's going to be easy because the two forces are more or less in the same direction. So I'm going to choose a coordinate system that's aligned with as many forces as possible, and that happens to be all of them. When you're putting your coordinate system on there, you are deciding what direction you're going to call positive and negative. Do so right there on your coordinate system. Next, you're going to break up any off-axis forces into components. This is where you'll do your trig. You'll take any off-axis forces and break them up into components. All right, that's drawing a free body diagram and setting up your free body diagram to solve your problem. So although so far I've only had 2 steps, you notice that all the steps have lots of subparts, right? Next, you're going to apply Newton's laws to each dimension. You chose which law to use at the very beginning. You're going to apply Newton's laws to each dimension. We said this was a first law problem. Because it's a first law problem, we're going to unequivocally state that the net force in the x direction is equal to 0 and the net force in the y direction is equal to 0. If it was a second law problem, then one of these would be set equal to 0 and one of them would be set equal to ma. But as this is a first law problem, we set both the net force in the x direction and the net force in the y direction equal to 0. Now, you're quite literally at the end of the set of steps, but it's understanding what this is telling you that's important. This summation is actually more like a set of instructions. It says, add up all of the forces in the y direction take into account their direction and set them equal to 0.